Hello, welcome back. I'm sure you are enjoying learning on embedded system design on ARM Cortex M4. If you haven't revised the previous sessions, please do go back and revise all the modules so you would be more familiar with using different peripherals and different registers associated with it, and you would be able to follow through. Today is day 26. You're going to learn about SPI. SPI is again a lengthy module, so I break that down to 2 days. So today is part 1. These are the sections you will learn today. So what is a SPI and how that is related with embedded system design, and how you're going to interface that with STM32F411, and then you're going to go and learn all about how the SPI works with the code. And today we will be learning to write the SPI GPIO initialization code, and we'll go from there. Before getting in, I would like to introduce myself. I am representing A2DG. It's a startup by Anbukarasu brothers. My brother Alex and myself are all in 2023. Both of us gathered over 20 plus years industry experience, and we would really like to put it out there so that it would be beneficial for you to shape you into a better professional. Our mission is to convey our knowledge to at least 100,000 future professionals through our online courses. And the main advantage is you can study from wherever you are, and that's really good about that. About me, I'm Arul P. Anbukarasu. You can call me as Arul or API, as persistent as I would like to be to share my knowledge and experience with you all. I have 20 plus years of experience working in various industries in Australia, Italy, Singapore and India, majoring on these renewable energy sector on solar and wind power conversions, power systems that related to lead acid batteries, network embedded systems that connected to ATMs, TCRs and point of sale machines, banking automation systems and smart parking operations. And my expertise lies in these 3 areas of embedded systems, VLSI and project management. I have a small announcement to make. I categorized into 2 different categories: the YouTube viewers and the internship professionals. In order to be eligible to get a free certificate, you have to attend at least 28 video sessions and watch it through. At the end of each and every session, there will be an attendance link. Please to click on that and fill your details and send it to us, and that will count for your attendance. Due to the regulations of YouTube, the videos can't live there forever in our channel on A2DG site channel. It will be removed after 2 or 3 days. So in case if you have missed out on one session, if you want to go back to do a recap, unfortunately miss out. That's why I really encourage you and advise you and recommend you to join one of our internship program that acquires you to get an internship certificate, and that's worth a lot, because when you land into that interview panel or after you got that first job, when you work with the senior engineers, they think this 30-day journey that you already put through, that you learned all the fundamentals and you had your hands on creating projects and verifying that projects worked with the hardware, everything, it all counts, because they don't have to teach you much, so you can just start from day 1 and be more productive with the team. Not only that, you will get your own login to log into our learning management system portal to go and check on each and every session. So once you finish, just click on complete. That will count for your attendance. On top of that, you will get unlimited access to course contents. That includes all the PDF materials, the source codes, the data sheet, reference manual, whatever you need for the series, for this course. And also unlimited access to all the course videos. You could pause the video and you can go and do something else, come back and watch it, or if you want to go back and revise something else, you can do so. It's yours. If you get stuck somewhere in the middle, please do contact our backend team, and they are a friendly team and they would be able to help you to make your journey go smoother along. So, shall we get into learn and see what the day falls out for us? I'm sure you are keen as I am. So let's get in and learn. Shall we? SPY. As you know, you have gone through this numerous times in your engineering degree, and you might have also heard from a lot of people out there, from the industrialists. So the SPY is abbreviated for Serial Peripheral Interface. The SPY bus allows, it is also another communication protocol. So the SPY bus allows the communication between one master device and one or more slave devices. So that is the basic difference between the other communication protocol that we learned, I2C. I2C can have multiple masters and multiple slaves, whereas in SPY it can have only one main master device, and it can have either one single slave device or multiple slave devices. And SPY works on a 4-wire configuration. So you need a serial clock, MOSI, MISO, and GPIO chip select. MOSI stands for master out slave in, MISO stands for master in slave out, and the chip select, like if you want to send the address from master to the slave devices, it only talks to the slave devices through the chip select, the slave select, as in this picture. So the slave select, it is nothing but the GPIO pin. So to control, and as you know, the slave can be interfaced with sensors like accelerometer or temperature sensor, whatever the case may be, or EPROMs, or even the memory locations. So the when it wants to communicate, so it will communicate from clock to clock, the connection is, and only the chip select controls the master, and that is connected to a GPIO. So this is the basic SPY definition. The slave device is a precision data converter, whereas the master device is the microcontroller. So you're going to interface that to the microcontroller with some measurements. So in this SPI series, you're also going to interface that with accelerometer, but you will cover that and you will learn that in the next part. But today we're going to learn the basics of SPY and all the registers associated with it, and then you will start to learn to code the initialization code. Also, when we talk about communication protocols, there are two communication, as you may remember, serial and parallel. When you compare between serial and parallel, SPY is a serial communication protocol, whereas because how you can compare with the parallel is, the parallel is much faster because at one time you can send 1 byte. So that means 8 bits can be sent in one instance, but it requires 8 different data lines. Whereas in SPY it is in a serial communication, so you can send 1 bit at a time, and you can do so by just 1 line. So you don't need 8 lines. So that's the major benefit. But being it's sent 1 bit at a time, occasionally you may feel that this could be slower compared to the I2C. So that is the basic difference between the serial and parallel. Now a small comparison with the SPY and the I2C compared to the USB 3s and 2s. As you can see, SPY is a synchronous serial, and the maximum device or the distance that it can connect up to is 10 feet. And the maximum speed is nothing but the frequency of the internal clock, the system clock, divided by 2. That's how the speed of transition of data, right? And in our program, we're going to use BRR register, and that's what determines the baud rate. And comparatively, when you see that into the I2C, it is also a synchronous serial, but the maximum distance is 18 feet, and it can work on high speed mode as well. Whereas the RS-232, 485 are in asynchronous, and they can shoot for long distance. Likewise with the Ethernet also, it can be connected to long distances, and its maximum speed is 10G. The USB 3 is simplex serial, and the USB 2 is half duplex type, as You are aware already all those terminologies of full duplex and half duplex and simplex. And Unit 3 USB 3G is connected, the maximum speed converts to 5G, and USB 2 can run up to 12 megabits per second. So these are all some of the examples that compare with the SPIs. So in other words, I2C and SPI is used for short distance communications, whereas the other protocols are used for long distance communications. So to summarize that, SPI and I2C, these peripherals communicate over the TTL logic, signaling in the voltage range of 0 to 5 volts, whereas protocols like CAN and RS485 communicate over a differential signaling, and that is well over 10 volts. That's the major difference. So that's why the SPI and I2C are short distance communication interfaces. So that's a summary. Now let's go into seeing about the SPI voltage levels. As you know, the voltage levels, whenever there is a waveform, high voltage is 1, that means it's on a on state, and if it is off, that means 0, the voltage is on the off state. So this is how the serial data is converted. And basically all the master and the slave should be running on the same voltage, but in some devices, if the master has to be operated on a separate voltage level and the slave has to be operated on a separate voltage level, then you need to have a voltage level translator which translates and connects to the required voltage levels to the devices. So if the master and the slave operate on different supply voltages, then with the use of voltage level translator, you can accompany that. And also, if you refer the data sheets, the voltage levels will be defined there. Between ground and VDD, you will have the voltage output high and voltage output low values, and the voltage input low and voltage input high values will be designed and defined in the data sheet. So please do follow the data sheet. It is a must, and you need to be familiar with all these terms. Now let's get into talk about the SPI a little bit in detail. As we just learned, SPI, the master controls the slave select and the serial clock. The SPI can have only one master but can have multiple slave devices. If it has 2 or more slave devices, that means it will have furthermore chip select lines. So only one can be connected at one time. And each slave has a slave select for independent control as well. And the data in here will be transmitted from master to slave or slave to master. That's the full duplex communication. Now let's see what is the slave select can be done. Slave select, this is the one, selects the slave device for communications. It is often considered as active low. So as you can see, there is a bar over SS, slave select, and this sometimes called by other names known as SL or CS bar, chip select bar, or chip select sync. In Texas Instruments you would see lowercase n and SS or SS hash. So commonly lot of data sheets you will see CS bar, that means it's active low or sync low, and it is used for the data converters, and you would see that in the TI devices that's used for data conversions. So that's the slave select bit pin. Next is the serial clock, which is this. The serial clock is the one that synchronizes all these clock and starts to do the data transmission between the master and the slave. And the serial clock originates from one master, and it can connect to the shared slaves. And also clock can be idle high or low. and data is clocked in either the rising edge or the falling edge of the clock. Also, other denotation, it can be sometimes called as SEK, and that's what the accelerometer has, SEK. Next is the master out slave pin. What is this? So this pin is an output pin. So it sends the output from the master, send the data to the slave, and connects to the MOSI pin. So it can be also connected to various slave devices as well. And in Texas Instruments and other some other microcontrollers, you will hear this as in different names as master, or from the slave device it's called as the slave device in, device input, device in, and SI from the master device. It's called as data out, D out, and serial out. That's serial in, serial out. So commonly labeled as data in T1 data converters. Next one is the master in, slave out. Here the difference is the output from the slave device used to send to the data to the master. So that's the difference. MOSI is the other way. MOSI sends data from master to slave. MISO sends data from slave to master, and it can also be shared with other slave devices. Slave output becomes high impedance when SS is not selected. So when you don't select this, then it can result in high impedance state. And also this is known from other names. From the slave device is SDO, DO, DOut, SO, and from the master device this can be also written as SDI, DI, DIN. So generally in the TI devices you would declare this as D out converters, data converters. So now let's go into learn about the clock polarity, C pole. As in this timing diagram, the chip select, as you know, it's always active low. So when you set the C pole as 0, that means the leading edge is rising edge, trailing edge is falling edge. So the other names for the leading edge is called the rising edge. The other name for falling edge is called the trailing edge. And if the serial clock is set, or if the serial clock is low, that's when the clock polarity is set to 0. But in the other case, when the serial clock is 1, then the clock polarity is set as 1. This means the reverse. Leading edge is falling edge and the rising edge is trailing edge. So it's the other way around. And data is read from left to right. So for each clock pulse, the leading edge is the first edge of the pulse, the leading edge. If it is clock polarity 0, then the leading edge is the rising edge. If the clock polarity equals 1, then the leading edge is the falling edge, or the falling edge. And the trailing edge is always the second pulse, the second pulse. So that's what the clock polarity is. That's what we just learned about the protocol bus modes, the SPI protocol bus modes. On C polarity, if it is 0, that indicates sampling on the first edge. If clock polarity is set to 1, that indicates the second edge of the sampling. Next is the clock phase. When the clock phase, what clock phase is, when the data is clocked, when C pole is 1 or C pole equal to 1, so 0 or 1, and the phase how it is generated and how it is linked. So in this case, in this timing diagram, when the CPHA is 0, that means data is clocked in all the leading edges, as you can see, data. So whatever this shows in the rising edge, that will fall to the CPHA 0 in this case. Data is set when SS falls low or at the previous trailing edge of serial clock. So for C pole of 0, this is the rising edge, and CPOL of 1, this is the same one, this will be the falling edge. So that's the clock phase 0. In clock phase 1, it's the other way around. Data is clocked on the trailing edge, meaning if CPOL 1 equals, if clock polarity equals 0, then this is in the falling edge. If clock polarity equals 1, then this is the rising edge. It's the other way around. So whatever the value there, and that's captures in the C clock phase 1. SPI mode has 4 different mode numbers, and we're going to use 0, 1 or 1, 0, anything that you wish. When you write polarity, clock polarity and the phase in 0, 0 mode, that means it's a 0 mode. 1 mode is clock polarity 0 and clock phase is 1. If clock polarity is 1 and clock phase is 0, then that's a SPI 2 mode. For 3 mode, both are 1. In this example, it's shown for 0, 1. So CPOL equal to 1, so that means on the trailing edge, clock phase 1 captures whatever data in there. So this is the mode numbers. And the protocol of CPOL and CPI, it's just an explanation from the continuation from the previous slide. If the clock polarity is set to 0, then the active state of clock is 1. The idle state of clock is 0. You can either write CPHI is 0 or CPHI is 1. If it is clock phase is 0, the data is captured on the rising edge and data is output on the falling edge. But if it is clock phase 1, data is captured on the falling edge and data output is on the rising edge. And the difference with the clock polarity is 1, then the active state of the clock is set to 0, the idle state becomes 1. In this case, it's the reverse of this condition. On the clock phase is 0, data is captured on the falling edge and the data out is rising edge. Clock phase is 1, data is captured on the rising edge and data output is on the falling edge. This is just a comparison between a single slave and a multi-slave. As you know, MOSI can be written also and denoted also as serial data in, serial data out. MISO is for serial data out, and chip select, slave select can be also used as a chip enable pin as well. So this is a single master single slave device, and this is the single master multiple slave device connection. So this is how it's connected. So the clock will be connected commonly from this, and MOSI will be connected to slave MOSI, and from the MISO it will be connected to the MISO, and you will have separate chip select lines, and everything is independent. So every line has to be controlled and connected to the following chip select line. So this is how it's connected. Yeah. And controlling about the multiple slaves, each device has an independent slave and it will connect through this chip slave select. S-clock, MISO and MOSI are each shared between the devices, so you can share that, but the chip select will have its own independent slave select. If device is not selected, MISO will go into high impedance mode, so it has to be in one of the select mode. And the controlling can also be done in another method called daisy chain. Daisy chain is nothing but the serial clock is connected as it is. The MOSI is connected to MOSI, but look at this MISO. The first MISO is connected to the second MOSI of the slave device. The second MISO is connected to the third MOSI of the slave device, and the third MISO is connected to the master. So this is like in a loop. That's why it's a daisy chain. It's almost everywhere. You will hear it in the industry. Daisy chain not only also relates to microcontroller, even if you do some group activity and if there is a link between one activity to the other, then that's also considered as a daisy chain. But again, you need to check with the data sheet and the particular microcontroller to see whether that SPI supports a daisy chain. If not, you need to go for the standard control measure the previous connections like this. And the meso is connected to the meso. So daisy chain is first this connection, and then the meso is connected to this meso. Now let's find out how it works with the protocol. First, the transaction is started by enabling the system clock. With the clock generator, it enables the clock. Then the SPI works with the shift register. The master sets the chip select line to 0, and then two registers of the same size are involved in the transmission, one in the master and one in the slave. Data is usually shifted out with the most significant bit first. Always the MSC goes out first. So for example, I'll explain in the next slide. And then at the same time, data from the slave is transmitted. Being a full duplex, it can also transmit back through via the shift register. It transmits back, and that's how the operation conducts. So if more data to be exchanged, the shift registers will be reloaded and the process of exchange will start again. When no more data is transmitted, the master will simply stop and toggle between the clock and the deselect slave line. So this is how the protocol works. And this is the one good explanation. First, you are sending the serial clock, you're generating the serial clock, then the shift register start its conversion. And the first conversion, you're going to send this B0 to here. So you already shifted the A0 to here. So likewise, you need to shift everything, A0, A1, A2, A3, A4, A2, A4, A7 in 8 iterations. So now the MOSI and the meso, so both the shift, using the shift registers, both the bits are transferred. So it's a full duplex. So this is how it is done. So when you transmit one data, the other one gets filled back. So I'll go here. This is the start. So now you're transmitting A0, and watch this. B0 will come here. When A1 goes here, then B1 will come here. Likewise, when A4 goes here, then B4 will go here. So nothing is left empty or vacant. So this is the SPI protocol. This is how it works. And again, we already heard about the full duplex. Full duplex stands for you can transmit and receive at the same time, and that's the full duplex configuration. And always the most significant bit is transmitted first or send data first, and then the LSB bit. The half duplex, you can determine whether it is a transmit or a receive. There is another method called simplex communication. In this, you can either only transmit or only receive. It can't be either or. It can be set just as a transmit or a receive. So that's a simplex communication. In the data sheet, you need to first go through the chip select and the D in and D out and see where they are all connected. So the timing diagram with D in and D out. A timing diagram shows us whole specifications and the relationships between the digital lines. Violating a timing specification can cause a failure because it may have runout error, timeout error, and this is how the SPI communication. The chip select has to be low and the clock is generated. Depends on the clock polarity and clock phase. The data in and data out is connected. So just to transfer 0 cross D2 on a MOSI and 0 cross 75 on the MOSI, this is how it's when chip select is active low on the rising edge. This is how the data gets transferred. So the binary value is 1101 0010, and that's nothing but 0 cross D2. And here the MOSI, the binary value is 0011 0101, and that's 0 cross 75. This is how being at the rising edge configuration. Now let's get into the timing. The timing, it has three different timing in SPI. The first is a setup time, then there is a hold time and a propagation delay. The SPI timing is nothing but is the minimum time required before the clocking edge starts, for which the data must be stable. So there must be some time set before the clock generated, so it will have some time to merge through to be latched correctly. So this is what it shows in the diagram, in the timing diagram, D in and D out. So this dotted lines, it's called the setup time. The state of D init is read into the device at the rising edge of the serial clock. So this is the setup time. Next one is the SPI switching, hold time and propagation delay, and these three pins are involved: serial clock, D in and D out. So that means in the serial clock, when the hold time is the minimum time required, after the clocking edge happens, then there is some time that's required for the data to be transmitted to be stable, so that extra time needing to adjust the clock, and that's what the hold time. So it has to hold or pause for a while to get that data. And then there is the propagation delay. SPI communication example. So this is an example with the chip select. When considering the S clock is in the low and data is clocked on the falling edge. Remember, if it is on low, then it is on the falling edge. And we're going to send D in as 81C3H to the device. And when you use that for every clock generation, you need to generate that. And the D out is nothing but whatever it gets on the falling edge, and that comes through. Here it's positive on state, so that's 1. Here it's on, but the data input is 0, but doesn't matter. This is 1, so this is also 1. This is 1. This is 1. But here the transition changes to 0, then 0. So 1. Likewise it's connected. And then this is the binary value for the D input, and this is the hexadecimal value. So this is how through SPI the data is sent and read. These are all some of the advantages and disadvantages. Advantages of the SPI is it's faster than asynchronous serial communication. The receive hardware can be simple used by shift registers, and it supports multiple peripherals like multiple slave devices. Whereas being data sent in one single line compared to the other communication mode, sometimes this can be defined as a slow moving SPI. So that's a small minor disadvantage. The controller must control all communication peripherals and can't talk directly to each other. That's another drawback. It usually requires a separate chip select line, so therefore you need extra lines to connect to each and every slave device. So these are all these disadvantages. Now let's see briefly or elaborately into where the SPI in STM32F411 is. STM32F411 slave select pin management. When you want the device to act as a slave mode, in the slave mode, remember the NSS work as a standard chip select in input and lets the slave communication with the master. But when a device is configured and to be used as a master mode, in the master mode, NSS can be used either as an output or an input. It depends. Being master has that extra luxury being used as an input or output, but in the slave mode, chip select can always be set as an input. So as an input can prevent multi-master bus collision. So that's the main reason, a master code to avoid the bus collision. So it has to be used as an output in that. And as an output, it can drive a slave signal of a single slave. These are all the SPI types of slave management. and the slave management is controlled through a software. In this configuration, slave select information is driven through this bit value, and the SPI is controlled by the control register. And the NSS pin is free from other applications use. So the hardware or the software select management can set using the SSM bit in the control register. That's the slave select management bit. SSM bit is slave select management bit. And this is the typical functional block diagram of the SPI, because both master and slave needs its own registers. So it will have a separate shift registers, and it will have its own RX buffer and the TX buffer. So that's how it's communicated. So always remember MSB first and LSB. The serial clock is generated and fed to the baud rate generator. This determines the frequency, the speed of the controller, and then the active low is connected to the master control logic. And with the communication control, this can be controlled over the control register 2, which has the TXC bit and the RXC receive not ready bit. And with the status register, it also has a TXC, and control register 2 is all used for the interrupts. Serial registers is all used for these bits, TXC, RXNE. And through this baud rate generator, between bits 2 to 0, you can set the value. You will see that in the program. And control register 1 will have the slave select management, and it will have the DFF. That's also main data frame format, because that's how the data is transferred through this bit, and RX only. So if you go to the functional block diagram, you can see the SPI peripheral bus connections. So you need to enable, okay, in this example we're going to connect and use SPI 1. SPI 1 is connected to APB2 peripheral bus, and we also going to use GPIO A bit. So we need to enable GPIO enable and the SPI enable, both clock axes. So this is how the frequency is calculated. As you know, the high speed internal line and the high speed external line and the phase lock loop all integrates to a mux and comes out as 16 megahertz. It put through to a bus prescaler with the 50 hertz APB1 cycle, the peripheral bus. As you know, the internal system clock is 16 megahertz, and if it comes to the SPI, it comes out as the minimum prescaler by 2, so you get as the 8 megahertz. So we're going to use the 8 megahertz value. And now let's go in to see some of the control registers, all the registers that's going to be associated and will be using in our program. And this is the control register 1. In this we'll be using the clock phase, clock polarity bit, the master bit, and this is the baud rate generator bit between bits 5, 4, 3, and then the slave select, internal slave select, and this is the slave select management or software slave management, I should say, and the data frame format and RX only. The others we are not going to use in this one, but we'll be using bit 0, 1, 2, 3, 4, 5 and 7, 8, 9 and 11. These are all the bits we'll be using in the program. And the control register 2 is used for interrupts. So if you want to generate any interrupts, then CR2 is used. And you can also check with the status register with these 3 mode: TXC, RXNE and busy mode, which is bit 1, 0 and 7th bit is the busy bit. So these 3 are used to check the status. And then the data register, that's where the data gets read from. So you need to use bit 1 and bit 0 and then bit 7, because these 3 are the status register, SR, SR1, so you need to use 107, the SPI register. And then there is also the SPI CRC register and the SPI transmit CRC register and the SPI I2SC function. This is the registers. The I2C prescaler register. This is where the prescale values are calculated. And now let's go into the schematic. This is the schematic of the ADXL 345. We're going to use port A for this program. So the STO is connected to MISO as PA6. The serial clock is connected to PA5. The serial data STA MOSI is connected to PA7. And the chip select can be any GPIO. So we are going to use PA9 as the chip select. And this is the pin configuration details. I already connected the hardware and it's ready to go. So please to purchase the hardware and practice with the hardware. Now you learned all the schematics and all the basics and everything in theory. So please go and have a couple of minutes break. When you come back, let's learn to write the SPI GPIO initialization code from scratch, and I'll show you line by line. So I'll see you back in a couple of minutes. So go and enjoy that break. I'll see you back shortly.